So, quantum neural networks 101. As I said, this is a little experiment or recompilation of tutorials and material that I found on the internet about this. So to understand quantum neural networks, the first thing is to also understand the classical neural networks that I think or I believe most of you know how they work, but just as a quick refresher, I'm going uh, to remind this. No, uh, classical neural networks are a classical machine learning model that is composed by perceptrons or neurons and the weights. Here we have the input layer from which we enter our data, for example, the weight and the height of a rat. And then the output is the classification or the regression task that we want to obtain. And then in the middle are a lot of hidden layers. Well, the perceptron only does a simple calculation, which is a weighted sum of the weights with the inputs of the previous layer, and it does an activation function. This is a very powerful model because with the activation function we can achieve to have nonlinear patterns in data and do classification tasks very fit to the data. And then we get our prediction y hat with a softmax or a sigmoid activation function, which gives a probability of obtaining one or another class. Just this. I'm not going to dig into it because it would take several hours. So, and then one key concept of neural networks that we're going to see it's very similar in quantum neural networks is the optimization part, because all the importance and all the power of these networks are the weights, which initially are randomly initialized, and then through an optimization algorithm that takes a loss function that compares the prediction with the real label. It optimizes these weights so that in the final model, when we input some data, we get the most correct outputs. And this is just a quick reminder. And then this is important for the experiment that we are going to see next, which is the encoding of images or embeddings that we're going to use, because what we're going to do is an experiment with Eurosat dataset, which is a dataset of satellite images, and we're going to try to do a classification task. But with quantum circuits, it's very complex to embed these images as we would do in a classical one, because they have only few qubits. So what we're going to do is to take the image and pass it through a convolutional neural network to get an embedding or a latent vector, which is very reduced in size, so we can use this as an input instead of the image itself, which could be very difficult. So we're going with quantum neural networks, which is a near-term QML model that it's the counterpart of the classical neural networks, and it's integrated in this field of classical data with quantum algorithms, although this is highlighted. No, it's this one. And even though it's similar, it's not the same as a neural networks, as quantum neural networks are not composed of perceptrons, and they don't like this. They don't have this network-like structure. So how do they really work? The first thing we have to know is that they're composed of parameterized quantum circuits that are also called variational forms or ansatses. These variational forms are just quantum circuits with gates that depend on the parameter. Typically, they're rotation gates because the parameter is the angle of rotation, and it's very easy to manage with. And one question that comes to mind with this is when we design a parameterized quantum circuit is if we can measure or we can compare one with another, or which is better. And we have two criteria to compare this one, which is expressibility and entangling capability. With expressibility, we refer to the coverage of the Hilbert space by the circuit's hypothesis space, which in Christian, it means the number of possibilities or the number of states that we can generate with our circuit. And we can see this with this Qiskit framework that, for example, for this circuit that uses a Hadamard gate, which leaves the qubit in a 50% state in the equator and a Z rotation gate. And if we sample this a lot of times, we get these shapes, this number of states that we can represent, that it's not very expressible. But with this circuit that we only add another rotation gate with another parameter, this is theta and phi, we can generate a lot more of states. And this is very powerful for QML models and especially for quantum neural networks that our model is as expressible as it can be. And then the entangling capability is the measure of how entangled our quantum circuit is. That is measured by this Meyer-Wallach measure. And it only means that if your qubits are not entangled, they have zero score on the Meyer-Wallach. And if they're fully entangled, like in a Bell state, they're they have 100%. And in this paper that it's very interesting, it suggests that there's a strong correlation between expressibility and the accuracy of our models, but not that strong with entangling capability. So it's more important to focus our efforts on expressibility. Everything right up to so far? Some question or some comments? Okay. I go on. If you have some comment, please just interrupt me as I said before. So the first part of a quantum neural network model is the most important, that is the data encoding or feature maps that are synonyms but not exactly the same. Because we have, as I said before, this very big problem with data encoding that is in this NISQ era that we're living. We have very few number of qubits, and our datasets, real datasets, have a big size, both in dimensionality or features and samples. Because I've seen a lot of experiments with the iris dataset or the wine dataset, but they're toy datasets and they're very little problems and they're easy to get to work. But an experiment that we're going to do with images is very different. So there are a lot of approaches to encoding on quantum circuits. I'm going to give two examples of them. For example, basis encoding, that it's just we take our features, but they have to be binary. And then each binary feature will correspond to a qubit. So if we have 14 or 15 features, we have to scale them to a binary mode, and then we would need 15 qubits, which is not very efficient because it scales linearly with the number of features. And then amplitude encoding is similar, but we use the data we're encoding as the amplitudes of the qubits. And this is a little more flexible because we would only need a logarithm of the number of samples by the number of features as the maximum qubits. But it's still difficult to scale because in the images dataset, it's still a lot of qubits to represent. So the quantum neural networks use what we call as arbitrary encoding, which are just the feature maps that use parameterized circuits to encode the data. We have here an example uh, of amplitude encoding that we embed all the dataset, including all the samples, in this initialization function. But as I said, it's badly scalable. And our feature map on the other side has all these parameterized gates, and we use each feature as the input for the angles and the parameters. So for example, in this one, we could have a dataset with 12 features, but only 3 qubits, which is very suitable for our problems. And yes, as I said, and there are a lot of pre-designed feature maps like this one, which is efficient 2. There's the set Pauli first order and the set Pauli second order ones. For example, this one has 3 qubits, but only allows to have 3 parameters or 3 features. And uh, I haven't found really any criteria for choosing one or another, or any characteristic that can distinguish between when we have to use one or another. So even you can build your own feature maps, and recently CSIC, I don't know, CIC, that has a recent paper that investigates the automatic generation of quantum feature maps for your specific use cases using genetic algorithms that I leave in the references, which is very interesting because the choice of the feature map is the most important one, because all the accuracy of the model depends on it, as we're going to see later in the experiment. And then we have the second part of the neural network, which is the variational circuit, also called ansatz, which is just a common parameterized circuit that can have as many gates as you need, and entanglements and everything. You can do your costume ones, or you can use the ones that are also pre-designed because they happen to perform very well and they're very well studied in literature. But it's worth to mention that as more long that you make your longer you make your layers and more gates you add, it's a higher risk of having decoherence in your in your circuit, and therefore to obtain wrong results. So it's preferable to have efficient and shorter ansatzes than longer ones. And then just the final QNN is just the combination of our feature map. These are our input data points that we feed into the feature map with the parameterized gates, and then we pass it through this ansatz to obtain our predicted labels. And it's not purely quantum because the classical part is the optimization function. As I said earlier, our ansatz or variational form resembles to the weights that we saw in the beginning with a classical neural network. So we have to optimize these weights, as well as we have to optimize the parameters in our ansatz with a classical optimization algorithm. And for this part, I'm not a great expert and not a great mathematician, and I have some workmates in my team that know a lot more about this topic than me. And for quantum neural networks, there are a lot of possibilities with other than gradient descent. That is the most known one, but there are a lot of even quantum-based optimization algorithms and non-gradient based, like SPSA, Covila, and other ones. But I'm not going to focus my attention to this because I'm not an expert and not a mathematician. So in this little experiment, yeah, we see just what we were talking about. We take a feature map which has 2 inputs, And then our real amplitudes ansatz that has 6 parameters to adjust. Well, this is a little comment because when you build a quantum neural network, what we do is measure all the qubits at the end. You don't measure uh, certain ones. And so if you have a multi-class classification problem, for example, 10 classes, you would need at least 4 qubits, because with 2 qubits you could obtain only 4 possible outcomes: 0, 0, 1, 1, 0, 1, and 1, 0. So if you need 3 classes, you would need already, or 5 classes, you would need 3 qubits, and so on. And then we build a sampler QNN, which is the internal implementation of QNN from Qiskit. I know there are another uh, frameworks, but the one used in this experiment is Qiskit. And as like in a classical neural network, we have a forward method which inputs the data into the circuit, and we get some output probabilities. Here we have as an initial point random weights, and we get a randomly prediction of 70% of one class and 29% of another. This is just as a little example, but we're going with our practical case. As in GMV, we often work with Earth observation data. I've chosen to use the Eurosat dataset, which is a dataset from Sentinel-2 satellite images with 27,000 labeled images and distant classes, which distinguish from buildings, crops, rivers, lakes, seas, forests, and many more. And I'm going to choose the version which is in RGB, not the multispectral band. And it's very suitable for our problem because it only is 64 by 64 pixels. And to simplify this problem, I'm going to choose only 3 of these 10 classes to make the classification problem easier, that are residential buildings, sea and lakes, and forests. Any question so far or comment? I've said something wrong, or is there something that you want to comment? All right. If everything's okay, all right. So we're going to import the libraries used for the experiment, some constants. Then I tried to execute this on IBM Q, but it was total failure because of the the long queues that make you wait for days even for this task, as I'm going to show later. The first thing, as I said, is transform our images into embeddings or bottleneck features with pre-trained convolutional neural network models. And we're going to get only, like in this image, this little vector, not that little, but this little vector that it's easily manageable rather than images. And then we load our data set. This is just an example of the classes that we're going to take: residential, sea lake, and forest. As you can see, the sea lake and forest images resemble a lot, which will be hard for the model, but we're going to see how it performs. And then after we've obtained our embeddings, we save them in a file. I've used 2 different models for testing, the EfficientNet and the ResNet. But still, these 2 models generate 2,048 long vectors and 2,500. So it's still a lot to fit the quantum neural network. So I applied some dimensionality reduction techniques to reduce the size of the dataset only to a 4-dimensional vector for each embedding. So I don't think this is very interesting for this workshop, but some feature selection techniques to reduce the size, and then I divide the data set into train and test. So we finally get what we wanted, which is 4 length vectors, and also I reduce the data set to only 900 samples because the original one was 9,000, so it was still a lot to feed our model efficiently. So we reduced the size, but this comes at a cost. It's possible that we lost a lot of information from the images in the process because it's not easy to transform an image to a 4-length vector. So what I do here is check the information loss, we can say, with the total explained variance from PCA. And we can see this number does not exactly represent the information value, but it somehow explains that we lost almost 40% of the total information in the original image. So this is a worth to take into account because it can explain many things. And then also, just to make it visual, I'm going to perform some k-nearest neighbors model to see if we've lost a lot of information, which we can clearly see if we take this sample from residential only with its embedding. We can clearly see that its most nearest neighbors are also from the same class, which is I was very happy to see this because I thought I lost a lot of information, and we can try this. Or I didn't execute the cells, so now it doesn't work. So, but we can clearly see that we haven't lost that much information, which is important. And here I just tried some classical models to compare with our quantum model, like support vector machines that have 91% accuracy, and the MLP classifier, which is even more important because it's the scale-learn class for neural networks. This is a neural network with only one hidden layer of 4 neurons, and then this solver, and we get 90% accuracy. So this is the most near approximation of a classical neural network that we have to compare with our quantum counterpart. And then we're going to build simply our quantum variational quantum classifier, which is the synonymous for quantum neural network. And these are different possibilities that I took into account that are from feature maps and for ansatses. So we can try, I've tried painfully a lot of these combinations, and not all of them work, like this set feature map that needs 4 qubits and these real amplitudes. The second one that is much more efficient because it only uses 2 qubits, and as we are going to see, it gives very better results. And these real amplitudes and sats, and we get our embedding input from these parameters. This one, and we can even try some weird stuff like this, but it's just a brute force approach. So we proceed with the training and assessing of results. First, the experiment that I chose with efficiency as the feature map and real amplitudes as the ansatz. That gives with the optimizer Covilla, because you can try with all of these optimizers that work very differently. And with this optimizer, we can clearly see that there is a plateau in the minimum, and that we get only 73% of accuracy, which is a lot lower than the classical models. And we can see here that it converges to this value and doesn't even go lower. And in the next one, these are some useful statistics and metrics for measuring the different classes and how it performed. For example, in residential, we can clearly see that it performs very well and not so much in Sea Lake, for example, just some metrics. And then I tried it with this set feature map and real amplitudes that has 4 qubits, and I expected this to work even better because the number of qubits is and the complexity of the model is even better, and we have 8 parameters instead of 6. But surprisingly, it worked very worse, and we get only 30%, 38%. But I didn't want, and I also tried this IBM-Q experiment, and it's curious to see. I wanted to show you because I oh, server connection thing. All right, because of the pending jobs that took a lot of time, I couldn't finish the experiment. But I think it's interesting to see how this model behaves in. Let's see if I can go to the jobs. All right. So to execute this model on the quantum computer, I just took 300 samples, 100 for each class. And what IBM does is it generates 100 different circuits for each sample, and it executes it each 100 by 100, so for each task. So you have to do 3 tasks to only do one epoch of our optimization problem. For just one optimization step, we have to do 3 tasks of 100 circuits, which takes very long in the queue, and then for the next another 3. So the I'm justifying myself from my own failure, but it was very interesting to do. And I tried with the IBM Q Keto that has this layout of qubits, and you can even choose the qubits you want that have the less error rate to try to avoid the coherence. But yes, this failed, so no. This is the simulator. This is why this is completely full, because I chose to to use the simulator, but it's not the same as the purely quantum one. Uh, well, then there was this attempt, because I didn't think it was fair to just compare the accuracies. I don't know if that's the correct approach to just compare the accuracy of our model that has 73% with the classical ones that clearly have a lot more of power and a lot more of literature. So I try to quantify if our model itself, without comparing to a classical model, would be powerful enough, or if it has some capabilities. And that's where I found this paper of the power of quantum neural networks that proposes a metric that can also be used for classical models, that measures the capacity of a quantum machine learning model for generalize and to find the and to be expressible with new data. And this is the global effective dimension and the local effective dimension metrics that I try to measure on my circuits. The global effective dimension computes with the model the untrained model with a lot of weights and random parameters with different input sizes, and it uses the Fisher information matrix and some other math stuff that uh, I don't deeply understand how well our model or expressive can be with any particular dataset. And the local one does it the same, but with our trained model, with our own data, with the trained parameters. It doesn't try a large number of parameters, but the trained ones. So I try to measure this circuit that clearly performed better. And what we can see, we try this model with 500 samples, 100, no, 5,000 samples, 8,000, 10,000, and so on with bigger sizes to see if this normalized score performs well. And we can clearly see that with as more data is used in the process, the expressibility or the generalization capability of our model increases to nearly 80%, which is very nice. And then with the local one that is needs to be trained, the last one wasn't trained, but with the local one we have to train our model again. Here we get a little bit better score. And using the weights trained afterwards the training process, we do the same, and we can compare that with the untrained weights. We get a little bit better results of generalization because the model has more possible outcomes. But with the trained model, it also reaches almost 80%. So it means that even though our model performed worse than classical models, and I wasn't able to find quantum advantage on these QNNs, really it has a lot of capability. Uh, I would like to know your opinion on this because I was very disappointed not to find the quantum advantage, and I made some conjectures. I made some hypotheses why this didn't work as expected, or if it even needed to work better. But I don't know if it was the choice of the feature map that I would need to build my own costume feature map, or I read that the initial point in the optimization algorithm is important because with some algorithms it can converge into plateaus. If it was quantum decoherence, or even if the choice of the feature selection and the encoding of the images was wrong. I don't know what you think. I know some of you are very experts on this, and I would like to know your opinion really on this, on why this didn't work as expected. I don't know if you have some idea.
If I can jump in, I've been working with these QNNs for a while, and the problems that you are seeing are the problems that the whole community is seeing right now. I mean, choosing better or worse feature maps is a problem even in classical machine learning. And the barren plateau problem is actually a huge problem with this kind of variational circuits or variational models. I can, if you want, send you maybe a small choice of literature that I've been gathering for a while already on my own, that talks about all of these problems, and maybe it can help you, trace a plan on how to solve them. But the literature on this is really extensive, and there's really not. I mean, there are several solutions to each of these problems, or several proposed solutions, but finding quantum advantage right now with this is almost impossible, I would say.
Uh,
And regarding the hardware that what you were talking about using, it's going to be impossible because think that you have to run a circuit every time you do an iteration of the circuit, and each time you do that, you have to re-wait for the
yes.
for the queue, so that's a little bit frustrating. And they have another way of using this hardware, which is called Qiskit runtime, which is the way we usually use the IBM hardware, but it's really expensive. I mean,
Yeah.
for QNNs, it should give good results because QNNs are naturally more robust to noise than other quantum algorithms, but it is expensive. I mean, we would be talking about thousands of euros just to run experiments like this. So I think that's a little bit of out of scope. I
Yes,
think that
I tried the free tier because I I wasn't planning on paying those quantities.
yeah. I think with simulators, you're gonna be fine for this. I mean, it might take a while. You've probably seen it, but the results with real hardware wouldn't be much different. I mean, I've seen real hardware for this kind of problems using Qiskit runtime, and they have error correction and everything, and the results are pretty similar in terms of numerical results. So with simulators, you can get a good idea on how these models perform.
So if I would be able to run this on these real quantum computers, I would get better results or better than the simulation ones.
Better in terms of time because they
Ah,
are still noisy devices. So the result would be pretty similar if you use error correction. It's well, error mitigation. It's quite similar. Uh, but the main problem is going to be the runtime that it takes to run the algorithm.
yes.
With the simulators might be a little bit slow, but it's the better option you have right now to use this kind of algorithms.
Okay. So this is not a very strange result that there is no quantum advantage in this problem. I saw specific problems like the iris data one that performed better or the wine data, but with this specific problem, it doesn't perform better. But
Yeah, that's
you
the
said
problem with machine learning in general.
yes, yes,
That it evolves through benchmarkings, and one day you get one result which is better for one data set, and then the same model performs worse for another data set. That's kind of a problem also in classical machine learning. And we still don't know enough about feature maps and kernels and how these barren plateaus actually work in the Hilbert space to to claim quantum advantage or to design even an experiment to claim quantum advantage with this kind of models or this kind of algorithms.
or well, I would be very interested in that references you took talked about.
Me too.
Sure, I
So thank
can
you.
I can upload them to the GMV drive. Maybe make a small folder for reference for
Perfect.
queuing and things. Yeah, no
Yes.
problem.
Perfect. All right.
Yes. So if I could make a comment, I guess I just basically seconding everything that Danielle has said, right? I guess one way to say why the results are not up to the expectations we had, well, I guess we do need to, I guess, manage a little bit our expectations, right? We have lots of uh, lots of things that can be optimized, and there, and I guess maybe one task is to find where there are potentials to see quantum advantages, but they're going to be hard to see. They're going to be hard to find, and yeah. So I guess we also have to manage this expectation a little bit, right? And they're not going to be found very easily with the hardware that's available, like I mean, worldwide available right now, right? So it's something in general to be known.
Yeah, I agree. That's why I thought if it was fair to compare yet at this time classical quantum models, classical models with these variational quantum classifiers in terms of accuracy because it's in an early state. So if we had to compare them, I don't know the metrics that we should use or how to compare these models without only focusing on accuracy or these metrics.
Maybe benchmarking models wouldn't be the, let's say, the most appropriate thing to do. Because between noise and runtime in the simulators, classical is going to win. And I mean, you are comparing it right now with a multi-layer perceptron from scikit-learn, but you can always make a bigger deep learning model using, I don't know, TensorFlow, PyTorch, or whatever you want,
Yeah.
and it's going to run labs around these algorithms.
Mhm.
So it's not really possible to be this to be deep learning right now with purely quantum algorithms. I think a good way to to continue with this line of work would be exploring these problems that you have highlighted. I mean, each of them is enough for a whole line of work, and I think being aware of the possible solutions that exist right now for each of these problems is a really complete work, and it's basically being on the front lines of the state of the art right now in variational quantum algorithms.
All right. Yeah, I totally agree on this. This future work on studying these problems and another encoding techniques, or even this AutoQML paper that proposes costume feature maps with genetic algorithms for each use case. It's very cutting edge, so it would be very great work to do in the future.